You're listening to the Anesthesia Patient Safety Podcast, the official podcast of the Anesthesia Patient Safety Foundation. We're bringing you the very best from the APSF newsletter and website, as well as the latest information in perioperative patient safety. Thanks for joining us.
Hello, and welcome back to the Anesthesia Patient Safety Podcast. My name is Allie Bechtel, and I'm your host. Thank you for joining us for another show. We have an exciting rapid response to questions from our readers episode today from the June 2025 APSF newsletter. This rapid response focuses on the carbon dioxide sensors for mainstream CO2 analysis for intubated and non-intubated patients developed by Nihon Kohden. There are two distinct models that include the CAP1 TG920P quantitative sensor and the CAP1 TG920P semi-quantitative sensor. There is a waveform display feature for both of these sensors that is compatible with all of their monitoring systems. These sensors have been primarily designed for monitoring respiration in non-operating room settings. The authors present two cases of patients receiving general anesthesia when the semi-quantitative CO2 sensor was used, leading to unrecognized CO2 rebreathing and respiratory acidosis. It is critical that anesthesia professionals understand the innovative technologies that are used in the operating room, including the uses and limitations, in order to keep patients safe during anesthesia care. Before we dive further into the episode today, we'd like to recognize Eagle, a major corporate supporter of APSF. Eagle has generously provided unrestricted support to further our vision that no one shall be harmed by anesthesia care. Thank you, Eagle. We wouldn't be able to do all that we do without you. Our featured article today is Beware of Semi-Quantitative Mainstream Carbon Dioxide Sensors in the Operating Room by Amrutha Nagella and colleagues. To follow along with us, head over to apsf.org and click on the newsletter heading. The first one down is the current newsletter. Then scroll down until you get to our featured article today. And I will include a link in the show notes as well. To help kick off the show today, we are going to hear from one of the authors. Here she is now.
Hi, I'm Amrutha Bindu Nagella. I work as a research scientist at University at Buffalo.
I asked Nagella what got her interested in this topic. Let's take a listen to what she had to say.
During my anesthetic practice in India, we encountered an unusual case with a carbon dioxide sensor in the operating room. A 34-year-old ASA1 patient undergoing anterior cervical discectomy developed respiratory acidosis despite standard anesthetic protocols. Soon after, in the same operating room, a 26-year-old ASA1 patient undergoing septoplasty also exhibited a similar pattern. The reason for this was not clear. In both cases, we observed that the end-tidal carbon dioxide values fluctuated with changes in the fresh gas flow, something that typically doesn't happen. This prompted a detailed troubleshooting process during which we identified the cause to be the carbon dioxide sensor which was used in both cases, that is CAP1 TG920P sensor. This miniaturized sensor provides only a semi-quantitative assessment of carbon dioxide and critically operates on the assumption that the inspired carbon dioxide levels are zero, meaning it cannot detect carbon dioxide rebreathing, an essential function during general anesthesia. We were unaware of the sensor's limitations and had inadvertently used it for intraoperative carbon dioxide monitoring.
Thank you so much to Nagella for helping to introduce this topic. Let's go into a little more detail about these cases now. The first case is a 34-year-old ASA1 patient who underwent anterior cervical discectomy under general anesthesia. The Datex Omida 9100C NXT workstation was used with a Nihon Kohden LifeScope 3562 monitor with a CAP1 TG920P CO2 analyzer. After IV induction and intubation, maintenance anesthesia involved 5% desflurane with oxygen and air mixture at a 1-to-1 ratio with a total fresh gas flow of 4 liters per minute for the first 15 minutes, which was decreased to 0.8 liters per minute after that. The displayed CO2 level on the monitor was 34 millimeters of mercury. 1 hour later, the displayed CO2 value during expiration had decreased to 8. Other hemodynamic parameters remained stable, with normal respiratory values for ventilatory parameters, airway pressures, and lung compliance. Increasing the fresh gas flow to 8 liters per minute led to an immediate change in the displayed CO2 value up to 33 millimeters of mercury. Throughout the case, the displayed expired CO2 values varied depending on the fresh gas flow. Check out Figure 1 for a visual representation of this. The next step involved an arterial blood gas sampling, which revealed a respiratory acidosis with a pH of 7.18 and PaCO2 of 60 millimeters of mercury. The anesthesia team discovered that the CO2 absorber appeared exhausted and replaced it. Now, check out Figure 2 in the article, which reveals that after changing the CO2 absorber, there was no longer any fluctuations in the displayed CO2 values depending on the fresh gas flow rates. The second case involves a 26-year-old ASA1 patient undergoing septoplasty in the same operating room with the same equipment as the first case. During general anesthesia, the same changes in displayed CO2 levels occurred. Decreased expired CO2 values corresponding to low fresh gas flows, with increased CO2 values when the fresh gas flows were increased. Once again, replacing the exhausted CO2 absorbent corrected this variation. Investigation by the anesthesia team into the CO2 analyzer revealed that the CAP1 mainstream sensor is a semi-quantitative CO2 analyzer that cannot be calibrated since it only contains a single CO2 sensor and assumes that the inspired air always has a 0 level of carbon dioxide. This semi-quantitative sensor is not designed to be used in the operating room during general anesthesia, and a semi-closed circle system with a CO2 absorber, since there is no inspired CO2 monitoring, which is critical to be able to detect rebreathing from a valve malfunction or absorbent depletion. Instead, these sensors are designed to be used in the ICU or recovery room where rebreathing does not occur. At the author's institution, these sensors were in fact moved from the ICU to the operating rooms. This experience highlights the need for anesthesia professionals to be involved in resource allocation and availability for these sensors and monitors in different hospital locations. We need to be using the correct monitor for the clinical care setting. The current information from the manufacturer states that the TG920P CO2 sensor kit is not recommended for patients receiving oxygen by mask. But what about for use with anesthesia breathing circuits? A safety tag from the manufacturer could state the following: not suitable for use with rebreathing systems in the operating room during anesthesia. Before we get to the response from the manufacturer, we are going to hear from the author again. I also asked Nagella what does she envision for the future with regards to this area. Here is her response.
Through this report, we wish to emphasize the need for clearer labeling and prominent safety warnings on the CAP1 TG920P sensor. A clearly visible tag stating not for use in the operating room could help prevent accidental misuse of the sensor in settings where accurate carbon dioxide monitoring becomes very crucial. Additionally, we also believe that a semi-quantitative carbon dioxide analyzer should not display a waveform. This sensor is designed to display a waveform that is compatible with standard monitors. The presence of a waveform creates an illusion of a real-time carbon dioxide monitoring both during inspiration and expiration, potentially misleading the anesthesiologist.
Thank you so much to Nagella for contributing to the show today. And now it's time to talk about the response from Nihon Kohden. The carbon dioxide sensors available from Nihon Kohden include the TG920P, which was used in the two cases, and the TG980P, which uses a different measurement method. The response from Nihon Kohden focuses on the differences between the measurement methods and the intended uses. Let's start with the TG920P series. Here are some of the important considerations for this sensor. For measurement, mainstream capnography that uses a semi-quantitative method which measures the CO2 partial pressure of expired air based on the assumption that the inspired air does not contain CO2. No calibration necessary since it is based on the premise that there is no CO2 in the inhaled air. Advantages include quick and easy to use, and in emergency situations, CO2 measurement can begin immediately. Limitations of this sensor series include in anesthesia circuits with depleted CO2 absorbers or a face mask with insufficient fresh gas flow when the inspired gas contains CO2, the displayed CO2 value will be lower than the actual CO2 concentration. There is an example of this in the operator's manual and in Figure 1 in the article. Additional considerations. Do not use this device when inspired air contains or may contain carbon dioxide gas. Any inspired CO2 that might be present is not measured or reported. Check out Figure 2 in the article for the caution supplied by Nihon Kohden in the operator's manual. It states, supply adequate oxygen when measuring CO2 partial pressure of a patient connected to a Jackson-Rees, Mapleson-D, or any other respiration circuit where CO2 gas may be present during inspiration. The semi-quantitative method measures CO2 partial pressure based on the assumption of no CO2 gas in the inspired air. It measures the CO2 partial pressure of the expiration of every respiration. If the inspired air contains CO2 gas, the measured CO2 value may be lower than the actual value. Now, let's turn our attention to the TG980P series. This sensor uses mainstream capnography with the quantitative measurement method with a single wave spectroscopic method. There is a required zero calibration of the CO2 measurement manually on the patient monitor interface that takes about 5 to 6 seconds before measurement begins. It is recommended for use in situations where the inspired air may contain CO2, but it can be used in situations where the inspired air does not contain CO2 as well. It is designed to be used during anesthesia care, mechanical ventilation in the ICU, and non-invasive respiratory management. There is accurate measurement of any CO2 partial pressure in the inspired air. As you can see, there are important differences between these two sensors. They are not interchangeable, and it is important to use the appropriate sensor that is designed for the specific clinical setting. Did you know that Nihon Kohden CO2 sensors use unique technology so that they can handle condensation without a heater? This means that they are smaller, lighter, and more robust than conventional mainstream sensors. Here is the conclusion to the response from Nihon Kohden. They write, Nihon Kohden is dedicated to improving the labeling of our devices to more clearly indicate the appropriate product in the presence of inspired air containing CO2. As a medical device manufacturer, we will continue not only to improve our product technology on a day-to-day basis, but also place a renewed emphasis on patient safety by working with anesthesia professionals on this matter in the future. Thank you for this valuable opportunity. Thank you to our anesthesia professionals and industry representatives for working together to bring us this rapid response article. This continued communication about the uses of medical devices and technology is important as we continue to work towards improved anesthesia patient safety. If you have any questions or comments from today's show, please email us at podcast@apsf.org. Please keep in mind that the information in this show is provided for informational purposes only and does not constitute medical or legal advice. We hope that you will visit apsf.org for detailed information and check out the show notes for links to all the topics we discussed today. The October 2025 APSF newsletter is almost here. But before the new newsletter drops, we hope that you will catch up on any of the articles from the June newsletter that you may have missed. What are you waiting for? Head over to apsf.org and click on the newsletter heading. The first one down is the current issue. You can also click on the APSF newsletter archives, and right at the top is the June 2025 newsletter. We hope that you will share the newsletter and this podcast with your colleagues and members of the perioperative team at your institution. Until next time, stay vigilant so that no one shall be harmed by anesthesia care.